Okay, everyone, I hope sound is loud and clear. It is 10:05 now, and we were planning to get started with this webinar at 10:05. I can still see people logging in, but in order to do not waste any time for any of the participants that are logged in already, we will get going and start with the presentation now. So today's webinar is again hosted by myself, Max Klosen. I was born and raised in Germany, have some practical experience as a carpenter in Germany, and then went on to university, studied timber engineering in Rosenheim, and later timber engineering in Vancouver at the University of BC. This webinar today is a quick outlook on recent CLT connection testing with cross-laminated timber in Vancouver here, a summary of the recent North American test data, and also summary of the proposed design procedures and values. First, we will be looking at panel to beam connection systems, which could be the connection between a diaphragm in a roof or floor assembly to the glulam post and beam structure. Or in the second phase, we will look at the panel to panel connections, which can be for shear walls or a roof or floor diaphragms. We will give a quick outlook on the statistics that we obtained from the testings, obtained failure modes, and some of the proposed values for design methods. So first, we will look at panel to beam connections, where we basically have a partially threaded screw driven in perpendicular to the face of the panel to give us a shear connection assembly. A second option would be to drive the fastener in at a 45-degree angle. This would be a fully threaded wood screw with much higher capacities and much higher stiffnesses, which we will be seeing in some of the test data later. For the initial testing, we basically used glulam centerpieces and CLT side members with a fastener in tension and a fastener in compression. These screws are arranged at 45-degree angles or 30-degree angles, depending what you want to achieve with your connection design, and are arranged in screw crosses in order to allow positive and negative load transfer, basically load transfer in both directions. In the second set of tests, we used glulam main members and glulam side members. This was sort of intended to simulate nail laminated timber connections. For those who do not know what nail laminated timber is, it's basically 2x4, 2x6, 2x8 material, or maybe 2x10 or 2x12 on edge nailed to form a large panel material similar to CLT. However, it's not cross-laminated. For the testing, we used a simple reaction frame with an actuator that pushed and pulled our specimen to apply load. On the right-hand side, we see the small reaction frame that tied our specimen to the strong concrete floor. We applied the Curie loading procedure, which consists out of trailing cycles and primary cycles. The trailing cycles are small displacements that happen after or before a primary cycle. We go through 6 load cycles here and then jump into a primary cycle where we increase the displacement and therefore the loading on the connection. Typical load displacement curves are seen or do look like this. The green lines are the standard cycles, and the black line is the backbone curve, which we use to explain some of the failure modes that happen in these connections a little bit later. We do see at the lower tail of the load displacement curves that is a little bit flatter, and the stiffness is different to the stiffnesses we obtained in the positive load cycle. So this happened because there was a little bit of deflection in the hold down steel beams here. We have to keep in mind that we talk about very small deflections here of only about 3 millimeters, and even if the steel beams just deflect 0.5 millimeter or 1 millimeter, we have an impact on our load displacement curves. So the typical curves again have load cycles and backbone curves or backbone curve plots in black and green. So this is what we use to determine the failure modes that we see. We do have the data gathered here and saw for these screw arrangements at 45 degrees with 8 screws or 4 screw crosses on each side of the specimen, around 143 kilonewton of capacity. If we double the amount of screws in our connection, we get around an 80% capacity increase for this particular test setup. For the stiffness, we basically see similar results. With more fasteners in the connection, we significantly increase the stiffness by up to 190% for this particular test. Similar results we see for the glue-lam side members. Remember, in the first setup we had CLT side members, in the second setup we have glue-lam side members with slightly shorter screws, but again driven in on 45-degree angles with 4 screw crosses or 8 screw crosses respectively. Again, capacity increase and stiffness increases are obtained with more fasteners in the connection. What we basically see, if we double the amount of fasteners, we do not double the connection capacity. This must indicate some sort of group action factor for these connections if they are loaded the way we loaded them. For the stiffness, we can basically say if we put in more fasteners into the connection, we will see less displacement and a much stiffer connection performance. In order to evaluate the failure modes of the connection testing, we basically took out the damaged and undamaged fasteners of the specimen as far as we could. So the first screw here is basically undamaged. It might have some micro damage inside the screw, which is not visible. So we only evaluated these fasteners for damage based on a visual appearance. The second screw here, we can clearly see it has torn off or failed in tension parallel to its axis. This indicates that at one point in time of the testing, the tensile capacity of the hardened steel was reached and the screw snapped off. If we want to look at how these fasteners are basically loaded and to what extent they are loaded, we look at the maximum achieved test capacity here of 143 kilonewton and compute how much load that would be per screw parallel to the screw axis. So we see that the screw takes around 25 kilonewton of load parallel to its screw axis in this test. And if we look at the design value that we can compute with the Canadian code approval for these fasteners, we would only see 6.86 kilonewton of withdrawal resistance of the fastener. For the design of these fasteners, we need to look at the factor tensile resistance as well. We have around 15 kilonewton tensile resistance and large safety factor compared to the axial load of the screw and the actual design load, or the design withdrawal resistance of the fastener and the factor tensile resistance. Other failure modes we saw are yielding and then snapping of the screws. So with the up and down motion of the actuator, we basically have forming a cavity around the fastener, and that allows the fastener to bend, crush wood, and then at the end snap off. The previously mentioned backbone curve is basically used to determine the failure modes here. So the load drops we can see are fairly small or rather large. Small load drops basically indicate that only a few screws snap off in tension, or maybe only one screw snaps off, and larger load drops indicate that we do have several fasteners failing at the same time. It can also be that many fasteners on one side of the specimen fail, and that will result in a very large load drop and a fatal failure of the connection. For systems where we have 16 screws or 8 screw crosses in the specimen, we do see that large load drops occur. However, we do also see that we have a fairly large residual load capacity after failure occurs, and the residual load capacity here is probably still in the range of the design resistance that we have. Among other failure modes, we see, of course, withdrawal resistance failure, which results in specimen separation in the shear plane. We do see head push out and head pull in failures of these screws. So head pull in and head push out are basically withdrawal resistance failures as well, because the threads basically cannot hold on to the wood and they get pushed in or pushed out or pulled in, sorry. Here we see the typical crumbled up wood fiber at a failure of withdrawal resistance failure or push out failure. And if we look at the same screw placement here, but in a higher density location near a knot, this was just by accident here, but it is a nice way of explaining this. The actual density and in this area was probably a lot lower than in this area, and we can still see that the threads cleanly bite into the wood, and there's no failure observed here. Fasteners and tension can also yield a little bit, so we do see some slight deflections or deformations of the screws in the shear plane, forming two plastic hinges basically that allow to deform the connection a little bit before it fails. In the second set of testing, we basically looked at a different screw arrangement where we have 30-degree screws. 30 degrees is basically measured between the glulam wood fiber in the centerpiece and the screw axis. So this is a much flatter screw-in angle that allows us to gain more capacities and stiffness compared to the 45-degree screw testing. Similar things we see for the glulam side members. So in the glulam side members with 30-degree screws, we have a capacity gain of around 30%, just like a stiffness gain for these connections as well of around 50%. So it seems like if we vary the screw angle to a much shallower angle, we the connections and also increase the stiffnesses of the connections. In regards to design capacities, we have basically taken the Canadian code approval, or you could also take one of the ICC approvals to calculate the capacities of these connections. The capacity for design here would be, or the design resistance would be 44 kilonewton roughly, and in the test we have seen 143 kilonewton, so we have an overstrength or safety factor of around 3. If we look at the stiffness performance, we do see that the stiffness calculation that we had in mind does not really match what we see in the testing. One factor for this could be that we have evaluated the test resistance and test stiffness at ultimate states, and the design resistance would be around 3 times lower, and we could probably look into only using 40 to 70% of the loads to derive the stiffness in a more linear range. Similar safety factors are derived from the testing of 8 screw crosses or 16 fasteners in the specimen. We see again a safety ratio of 3 when we compare the design capacity to the test resistance. We do want to mention here that for our design approach, we have not considered the dynamic loading or load cycles that we saw. Some of the specimen or most of the specimens saw around 50 load cycles, positive and negative in average, until failure occurred. So this is not considered in the design procedure. We basically use standard term loading here, with the KD factor for short-term loading being 1.15. For the 30-degree screw arrangements, we see one more failure mode that is pretty interesting, and we have to carefully consider this in design approaches and steps. So what we basically see is a shear failure parallel to the grain in the glulam centerpiece, which looks like this, an entirely separation parallel to the grain. This mostly happened right at the screw tips, where the stresses are released back into the wood. So what we need to assume is that the stresses are transferred along the screw axis here, and at one point they will be released back into the wood, which causes the wood to fail in parallel to grain shear. And this is definitely something we need to consider when we design with these fasteners. Load displacement curves look very similar for the 30-degree screw-in angles. We have steep load drops, steep capacity increases, and we can always nicely see in the backbone curve when fasteners fail. A very steep load drop is of course observed if we have complete separation or shear failure parallel to the timber element here, to the glulam beam. This would basically indicate a fatal failure of the connection and no residual capacity left. For the testing, we have had a short specimen here, and we were not able to allow the ideal placement of the fasteners. Ideal would be if we can always intersect the fasteners in the shear plane. For these small tests, we did not have enough space in the specimen to do this for all the testing. So we have done basically what we could and arranged the fasteners as possible. In the second step, we will be looking at the panel-to-panel connection now. So panel-to-panel connections, again, could be a diaphragm for floor or roof, or even CLT wall assemblies built as a shear wall. The first series here looked at a three-member connection with several connections in between, and the second set of testing looked at a plain shear application with only two members. I will walk you through the boundary conditions that were considered in this testing. The first one was basically the standard CLT panel with a surface spline with various thicknesses. We had lap joints where basically the CLT panel is notched out and overlapping the other one. And we have also looked into the plain butt joint connections, a variety of 3-ply panels and 5-ply panels. Plywood thicknesses for the surface ply connections ranged between 3/4 inch of plywood and 1 inch of plywood. And because we have considered different CLT thicknesses, we had to consider different fastener lengths to engage the fastener in proper load transformation. Also, we have varied the amount of fasteners in the connection with different numbers of screw rows. So there were specimens with only 1 row of screws and specimens with 2 rows of screws, basically double the amount of fasteners. Furthermore, we looked at the plane shear performance. This means that the shear force is basically perpendicular to the fastener axis. And also we looked at the inclined screw arrangements where the force is on an angle to the actual fastener axis. In regards to spacings in CLT, we see some interesting facts. So in CLT, we can place the fasteners very close to each other. The wood is not that likely to split due to the cross layers of the CLT. However, if we connect CLT panels to beam members, we need to make sure we understand that the spacings in the glulam member below will basically be in control of the spacing requirements for the connection. Here, a quick walkthrough for the CLT connection setups. We have basically a CLT panel with 1 row of screws and a surface spline made from plywood 3/4 inch. We do have 2 rows of screws, double the amount of fasteners in the connection. We do have half-lap joints with 5 fasteners per sheared lane in 3-ply panel and 5-ply panel. And then we go from the plain shear applications to withdrawal resistance applications, where we basically have 2 sets of screws driven in opposite directions on 45-degree angles to engage the fastener's withdrawal resistance rather than its plain shear resistance. The last approach is to butt joint panels. This could be in an industrial setting where visual appearance is not that important and cost is of major importance. So the idea here is to reduce the manufacturing cost on the CLT panels by just stitching them together with full thread screws on a simple unmachined butt joint. The testing for the 3 panel members was with a simple actuator pushing down from the top. It is a displacement controlled loading procedure. We do assume failure of the connection after the load dropped to around 80% of the recorded peak load, and data recorded is of course the actuator force or load and displacement at 2 spots in the shear plane. Some of the capacities that we see for surface splines with 1 row of fasteners are around 4.1 kilonewton per pair of screws. We selected pair of screws because we wanted to compare it to the actual pairs of screws arranged at 45-degree angles. We always have a pair there because we have 1 fastener in tension and 1 fastener in compression with these arrangements. For the surface spline connections with 2 rows, we basically see a decrease of capacity per pair of screws. This is due to the higher number of screws in the connection, and we do also see higher stiffness in these connections. So it seems, or it appears, like if we put in more fasteners in these regular shear connections, we do also see higher stiffness. For the lap joints, we have, again, one row, see around 10.3 kilonewton per pair of screws in resistance, and similar resistances for the 45-degree screw arrangements. If we evaluate this, we have to always look at the actual number of fasteners in there, because we are always comparing it to a pair of screws. We need to make sure that we do not skew the results. In general, we can always see that the fasteners in tension provide a much stiffer approach of the connection, so we get very high stiffnesses and high capacities out of this. The consequence of this is that we have a very small displacement, of course, and potentially very little yielding in the system. For the last set of the double inclined angle with the butt joint, we see similar performances. It is again apparent that the screws are utilized in tension and therefore provide high capacities and high stiffnesses. For this particular set of testing, we could also allow for a force in this direction. The fasteners are basically driven in cross angles here, and could also allow for out of plane load transformation load transfer if required. In regards to ductility of these connections, we need to be careful on how we evaluate this. There is one approach listed with FEMA 356. This approach seems reasonable for the regular shear connections. However, it does not necessarily seem reasonable for all the connections in tension here, because we do get ductility values here which seem very high. But if we look at the actual load displacement curves, which we will do in a little bit, we do not see that much deformation in the connections. For 5-ply panels, we have similar observations. We have larger embedments in the 5-ply panels, so we gain a little bit of capacity in it compared to the 3-ply panel systems. Also, a little bit of stiffness is lost or gained depending on how we compare the specimen. What we basically see is that for 5-ply panels, we can almost double the capacity due to the fact that we allow for more embedment in the specimen and can actually utilize the full yielding strengths of the fasteners. For the surface ply connections, we have to understand that in the 3-ply panel, we used the 3/4-inch plywood spline, and in the 5-ply panels, we used basically a 1-inch surface spline, and with a thicker surface spline, we basically allow the connection to take more load, which basically tells us that in surface spline connections, the connection capacity is controlled by the plywood thickness. In the 45-degree screw arrangements with fasteners in tension, we mostly see pull-out failures. We did not see a lot of tensile resistance failures, just because the embedment depth is not enough in CLT, in the thin CLT panels, to allow the fastener to fail in tension. Overall, we can conclude that for lap joints or surface ply connections where the fastener is used in tension, we basically get high stiffnesses and high capacities compared to regular shear connections. Looking at some of the obtained load displacement curves for shear connection systems, we see a flat performance for all these systems where we have 1 row of screws or 2 rows of screws, or where we have a 1-inch or 3/4-inch plywood thickness. So clearly we can basically say that for all these surface ply connections, we have small differences regardless of the panel thickness, of the CLT panel thickness. It seems that the plywood thickness has a large impact, of course, on these connections, and by varying the plywood thickness, we can potentially get a much better connection performance. Looking at lap joints, we can see that lap joints have a different performance here already. We can see a big difference between 3-ply and 5-ply panels. In particular, in the very first phase of the testing, we see a much steeper load increase compared to the plywood joints here, and we see a big load jump between 3-ply panel connections and 5-ply panel connections. The steep load increase here, or resistance increase for the 5-ply panels, results out of an embedment depth, of course, and also due to the fact that we have parallel to grain loading in the 5-ply panel in the shear plane. For connections where we have lap joints with fasteners in tension, we again see a really steep load increase and a fairly brittle performance here at the end of the testing compared to the regular shear applications. If we look into the 5-ply panel connections now, we see even more capacity per pair of screws, and again, not a lot of deformation and deflection in the connection, not a lot of ductility, a rather steep load drop at the end of the testing. For the stitching joints, basically the butt joints with double inclined 45-degree screw-in angles, we see an intermediate performance between 3 and 5 plies here, with again a steep load increase and a rather brittle performance at the end of the test. Here we have some of the test statistics. This will be available to you later in the PDF file as well. You can see the amount of fasteners that we used in the testing and all the values that we obtained from the testing in regards to deformations at certain points, loads at certain points, and the obtained stiffnesses. More interestingly, we want to look at the design resistances here that we obtained from the design approach that we figured out for these systems. So in this column, we will always see the design resistances, the estimated displacements, and for the estimated design displacements, we need to again make this note here that we have evaluated the testing here based on ultimate deformations and ultimate test load, and in our design, we only take a fraction of the ultimate test load into account. So these results here may be skewed a little bit and not reflect what actually happens in a real structure because the loads are much higher here. What is easy now is to derive overstrength factors. So we can see that the overstrength factors range anywhere from between 2.2 to somewhere to 9 for the lap joints in particular there, where 9 seems very, very high in terms of overstrengths. An explanation for the high overstrengths here, I want to explain this quickly, could be that there are heavy reduction factors in Canadian design here. The LPJ factor, I believe it's a factor for a limited penetration. So if you have less than 8 times D penetration into the main member, you get penalized with a certain factor that reduces your capacity. So this might be one of the factors that influences the high overstrength factors here. Again, what we see for the tension connections here with the red circles is that our design stiffness estimate doesn't really match what we see in the testing. This might be due to the fact that we have very small displacements for the assumed or design loads here that does not match the actual high test values there. If we display this in a chart, we can see the experimental data and the design data here and see a large overstrength factor for pretty much all the connections. Some of the failure modes that happened in the CLT panels here are closing of the gaps and opening of gaps, basically out of plane or in plane deformation, opening up the joints a little bit and having definitely an influence on data that we obtained. The surface ply connections seem to perform in a very ductile fashion. We probably have around 50 millimeters displacement here that the actuator pushed down before the specimen was assumed to fail, with a lot of plywood splitting, crushing, and closing and opening of gaps and checks. These screws here basically show the yielding of the fastener and the plywoods. We can see very small yielding here only. So if we were to increase the plywood thickness a little bit, we can probably see a much more pronounced yielding of the screws in these connections. In the in the half lap joints of 3-ply and 5-ply panels, we basically see more yielding in the screws and actually also breaking of screws after a large deformation. For the second set of testing, we looked at the approach from Bradner, which basically subjects the panel to a plane shear load. We again looked at a variety of different connection systems here with surface ply joints, lap joints, butt joints. Again, we looked at a new factor here and try to eliminate the friction. So all specimens that are labeled NF is no friction. There was an anti-friction membrane applied in the shear plane, which we will show in some of the images in a little bit. We also looked at, again, a different variety of screw lengths and screw combinations, different screw-in angles for shear, withdrawal, and particularly interesting, a combination of shear and withdrawal screws, which are intended to provide a little bit more ductility in a connection where full thread screws are used in tension. Here, just a quick overview of the specimen that were used. So on the left-hand side, we always see the specimen with intended friction in the shear plane. And to the right-hand side, we see the specimens with the anti-friction membrane in the shear plane, which was intended to eliminate friction. Half-lap joints look similar. Same applies to the half-lap joints where fasteners are arranged at 45-degree angles with screw crosses. Here's the rather interesting application. We basically have screws in withdrawal applications here, and in the center of the specimen there are screws arranged at 90 degrees to the shear plane, which are intended to increase the ductility of the connection system. Again, we completed a test series with the double inclined angle and the butt joint testing. A loading procedure for this was selected to follow a European test standard DIN 26891, which basically goes like this. We load up the specimen to 40% of the approximated maximum load. We hold the load there for 30 seconds. We unload the specimen to around 10% of the approximated estimated maximum, and hold the load again for 30 seconds. And after that, the load is basically loaded to failure. Displacement measurements were taken at the front of the specimen and at the back or rear of the specimen, and the average between those two measurements was taken to determine the displacement of the connection. Failure modes we see in these systems are basically head pull-in of the screws into the plywood up to a state where the plywood entirely separated or almost entirely separated from the CLTs and indicated ultimate failure of the connection. For the half-lap joints, we see some out-of-plane rotation, fastener yielding, some head pulls in, and so on, and a large displacement of the connection before or under load before failure really was determined. For the screw crosses with fasteners arranged at 45-degree angles in opposite directions, we do see head pull-in and head push-out failures of the fasteners. For the last set of testing, where we have the stitching of the panel joint with the double inclined angle, we always see some out-of-plane rotation, which is resulting from eccentricities in the connection, and also deformations and separations in the shear planes. Here are some of the results summarized. We basically concluded or can conclude or intend to conclude that the effect of friction in these joints seems to be very small. We do not see large load or resistance differences between connections where friction occurred and where friction was intended to be eliminated with the anti-friction membrane. So it appears that the friction has not a real big impact. Again, 45-degree screws are rather brittle. We get small ductility values here, and it seems like for screw combinations of 45 and 90 degree, we can significantly increase our ductility ratios or the performance of the connection in terms of deformation under load. Comparing these results between 5-ply panels and 3-ply panels is what we do with this slide. We see around 1.5 times more load in the 5-ply panels than we do see in the 3-ply panels. Interesting is to look at the load displacement curves that were obtained. This is the load displacement curve with friction. The second curve here is without friction for the surface plying connections. This is the curve with friction for half-lap joints and screws in shear. And here we see the half-lap joint with screws in shear and no friction applied. So what we see, there seems to be no impact of friction on these connections, which is indicated with the load displacement curves and the previously analyzed data. Again, we see the same stiffness performance here initially with the connection, we get a much higher stiffness, initial stiffness for the half-lap joints than we get with the surface planar joints. For screws in tension, we again see a fairly stiff performance and a rather steep load drop at the end, where we have a slight difference between 45-degree screws with friction and 45-degree screws without friction. All curves for fasteners in tension give us an almost linear stiffness increase and then a fairly brittle load drop at the end. Interestingly, for the systems where we used fasteners in tension with screw crosses, full thread screws, and then fasteners in shear here with a partially threaded screw, we see a very nice steep load increase here, initial stiffness of the connection with a fairly long flattened curve for displacement. So we have around 1 inch of displacement here basically before the connection fails, while we would be able to utilize this stiffness here in the design as well. Friction, again, seems to have very small impact on this setup as well. For the stitching joint, butt joint, we see intermediate performances. Basically, we have, again, steep load increases with very small ductility at the end. Also, friction does not seem to have a large impact here as well. So basically go and say there's not a lot of impact of friction in these connection systems here from the test data we have for now. For the 5-ply panels, we see similar performances, of course. That is what we kind of expected already. Again, we see a steep load increase from surface ply to half-lap joints and 5-ply panels. With a steeper load increase here at the origin of the test or initially. And of course, we again see a fairly steep load increase for the joints with half-lap and screws in tension. 5-ply panels indicate the same results for the screw combinations of tension screw and shear screws. We have around 10 millimeters of displacement in this compared to the only 5 or 4 millimeters of displacement in the other joints while maintaining the initial stiffness. I assume if we were to put in a few more screw crosses in tension here, maybe 1 or 2, we could potentially go up to the load level here and then receive a flattened off what I was just doing here. Looking at the data obtained from this test, we can basically again look at the different numbers of screws that we have in the tests, and again want to mention that it is important where we evaluate the stiffnesses here to compare our design stiffnesses to the actual tested stiffnesses. Design resistances are listed in this table. Predicted design resistance. Again, overstrength factors are calculated for these design resistances. We can again see a significant large number here for the half-lap joints, which again could result out of the heavy penalty that we get from the JPL, the reduced penetration factor in the main member, which is, I believe, around 0.625. So we reduce our capacities there by 40%, and therefore we get a very high overstrength factors. The other overstrength factors range between 3.4 and 5, which is probably a reasonable assumption for many of these systems. Again, we see small displacements following our design approach, and therefore rather high stiffnesses in our estimate. For the 45 and 90 degree screw arrangements where the fasteners are combined, we have entirely neglected the 90 degree screws. So for our design and the load transfer, we only assumed the fasteners in tension and compression here, which are fully threaded wood screws, to be active in load transmission. Towards the end of this presentation, we just want to show the different performances again of fasteners basically loaded in half-lap joints where we have a relatively reasonable stiffness increase initially, and then a curve that keeps flattening down towards more displacement at the end. All fasteners where all connections where fasteners are used in tension have a stiff performance with a fairly steep load drop towards the end of the testing. For the connection systems where we have a combination of screws, 45 and 90-degree screws, screws in tension and screws in shear action, it looks like we get very good initial stiffnesses and still are able to maintain some sort of displacement and ductility for larger deformations in this area. Again, we show the bar chart here that gives you an idea on where design resistances are and experimental data is. So we can definitely say we have a lot of overstrengths in these systems, which is not always a good thing. Actually, if we underestimate the capacities and deformations of our connections by too much, it could change the system performance, and we definitely have to look into these systems here and see what the most reasonable approach is to make shear walls or diaphragms yield at the intended load level. Overall, we can conclude that the Series 1, where we have used three panels in the testing, was probably not as appropriate as we initially figured. There is a lot of interaction in these areas here. A lot of friction is developed probably down here due to wedging of the members. We saw some plywood splitting in these areas. Screws pulled heavily into the specimen, and there was a lot of factors that contributed to the connection performance in the first test series. The intention here was that we thought if we have three members there, it's probably closer to the performance a diaphragm would have, because there will not only be one panel in the diaphragm, but many panels connect to each other with lots of impacts on performances. Comparing our design data to the data that we have from Series 2, it seems much more reasonable to compare to that and to get a clean understanding of how the systems perform if only a shear load is applied in the shear plane without a lot of interaction on the testing and the connection performance from splitting plywood, frictions, opening up of gaps, and so on. This is pretty much the end of the presentation. I want to express a lot of gratitude to Professor Dr. Thomas Tannert from UBC. He's the researcher in charge of this research project, organized funding for it, and provided help in data analysis and preparing data for this webinar. Also, I want to definitely thank Afrin Hossain. She is the PhD student at the University of BC, looking into these connection systems, and will finish her PhD degree within the next few years on this particular topic. Thank you also for the supply of the CLT members from CLT and glue lamp manufacturers here in British Columbia, and funding that was organized from UBC to conduct this research project. This it is so far from our end on the structural screw technology in tall wood buildings. Tall wood buildings will use CLT members and glue lamp members, so we do hope that these obtained test data are applicable to some of you, and that potentially some projects in the near future utilize some of the data we have gathered with this research project. One quick announcement for MTC. Many people do not really know what MTC does, so I will quickly explain this in 2 sentences. MTC is a modern timber connection supplier. We obtain all our connection systems from Europe, are trying to get code approvals for these systems in North America, and provide technical consulting for engineers like you that use these systems for the first time. So if you want to use some of these products in your design in the future because you think it's the appropriate fastener to give you a cost-efficient connection design, please feel free to contact us, and we will hook you up with our technical people to help you design these systems. So this is it from my end now. Thank you very much for attending. I hope it was useful information, and we will stick around a little bit until all the questions or most of the questions are answered. Thank you very much for attending, and we will see you soon. Thank you. Goodbye. So there's one question here. I hope you can all hear me still. There's one question. If we applied some sort of loop or grease at the shear plane, I do not think there was any loop applied. It was basically just the anti-friction membrane or foil that tried to eliminate the friction. So one question here. If CLT panels were tested with a notch at the panel connection for gravity load. So notches, I would say, first of all, we did not test this. Notches are kind of always a little bit dangerous in wood because splitting perpendicular to grain issues. So if we were to test some of these connections, we would definitely need to think about reinforcements in these areas to avoid splitting perpendicular to grain. We have not done this testing, but we would definitely like to look into this and follow up with you on this question and find an appropriate answer for that. So I just hear that Dr. Tannert from UBC confirmed that there was no loop or grease used in the shear planes there. One question to the length of the specimen parallel to the load, if that has an impact on the connections. Not sure if we can answer this from this testing here. We used fairly short specimen with small spacings to determine on how the fasteners perform at the connection and in the shear plane. I would assume that a long CLT panel does not provide too much more difference if we use the same amount of fasteners in it. However, this would probably be something that has to be confirmed in a larger scale test. There's a question from Ben. I'll try to dig this up. Seems to be there's a question from Ben. Could you elaborate on why it is ideal to have the cross screws intersect at the shear plane? First of all, there might be some eccentricities in these systems. So that is at least what we figured from our initial analysis. If we place the fasteners in the shear plane or in a way that they intersect in the shear plane, we have a balanced out system and basically always the same forces in all directions. So from the assumption that we made for this comment, it was just the idea of having everything balanced out and the forces all lined up properly without any potential eccentricities. Yes, slides will be available after the presentation. So I believe the webinar will be, the webinar is recorded, absolutely, and you will have access to the webinar slides on our webpage as soon as it is uploaded. You will also be receiving an email with a PDF file that shows some of the slides and some of the results that we have. Right now, there's no software available in North America to design these connections. What we do have, however, a CLT connection design guide where we designed these connections following certain assumptions already. You can go to our webpage into the appropriate section and download the white papers or the design guides from the resource section on our webpage. Okay, so here we have one more confirmation from Dr. Tannert. Thank you, Dr. Tannert, for addressing this. So last year there was testing on at UBC with 1.5 meter long panels where the results were apparently similar to what we have in the small scale tests here. So that was a question that was raised here. I hope this is answered with this comment. Yes, there is one question here if the predicted results that we have are calculated with the Canadian code approval. Yes, the results are calculated following the Canadian code approval. However, you have to adjust the embedment strengths for regular glue laminated timber or lumber to what we have in CLT. CLT has cross layers, and therefore we always have a mix between parallel and perpendicular to grain loading in the shear plane there, and need to adjust our embedment strengths for this. So there's one question here if the test results here yield or lead us to introduce changes to the design process in evaluation reports. This is a question that we would definitely have to address. I believe we are very conservative with our estimates in terms of capacity. For most of the connections, we see at least an overstrength factor of 3 or higher. This basically means that we are designing on the very safe end with the current code approval. I would definitely like to look into coming up with more aggressive equations a little bit to allow for more accurate predictions of the CLT performance systems there. So there will be probably a little bit more testing needed to derive design equations or adjust design equations with factors, but this is exactly what we are trying to do with the PhD project here to determine if the currently used design procedures are too conservative or too aggressive. So one question here on CLT panels. If we did test CLT panels for in-plane tension, we did not test any panels for in-plane tension. I believe, if I'm not mistaken, there is a test project right now going in Canada with FP Innovations. This would probably have to be confirmed by us or some other people that are involved in this testing. We do not test the CLT panels itself. We have only tested the CLT connections. There's one question here if the estimated results contain or include the resistance factor materials. We have basically, for the design procedure, we have basically followed the CSA 086 respective code approvals and basically plugged in values into the Johansen yield equations that you find for lag screws or wood screws in the Canadian code. These equations have safety factors, for instance, the 5 factor of 0.6, which we of course applied to the design values. So if this is the question on this topic, we have applied safety factors, of course, to the design values following the lag screw design procedures of the CSA 086. One question here, I'm not sure if I understand this correctly, so we may want to follow up with Richard there later today and see if we can sort out this particular question on the in-plane tension between CLT panels. So what we have tested now is basically a force component parallel to the shear plane and not perpendicular to the shear plane. So if you are intending to design the connection perpendicular to the shear plane, we have not done testing in this direction, but I do assume the design approach that we have used applies to this loading direction as well if we do appropriate adjustments to the factors that go into the equations. So there's one question here from Simon. If we basically saw a group factor in the connection systems, so from the data we have now and the initial data analysis, it looks like there is some sort of group factor for all screw connections where we have many screws in one connection. For the very beginning of the presentation, we covered this a little bit. So if we double the amount of fasteners in the connection where screws are used in tension, so say we have a 3-ply CLT panel connecting to a glulam beam, and we are using, say, 8mm by 300mm screws on 45-degree angles in tension, and we have 8 screws in this connection, we would probably see around 140 kilonewton of capacity. If we double the amount of screws, we see, I believe, 260 kilonewton in capacity. So we do have some sort of group interaction here, which does not quite yield double the capacity when we are doubling the amount of fasteners. Same applies potentially to the shear connection systems where fasteners are loaded in plane shear actions. If you wish, we could definitely look at this. We would basically need to know if or what the particular connection is you're looking at, and then we could forward you the respective tables from the testing and make a judgment call on what kind of group action factor we see in these systems. For our design values listed here, we did apply a group action factor. Basically, we went into the CSA OED6 again, applied the JG factor, which is the group factor, group reduction factor for the CLT connection systems as per design code. In some areas, it might be a little bit over conservative as the JG gets very small, 0.8 or 0.7 in some areas. So you have a 30% reduction of capacity there and to largely increase the amount of fasteners in your connection. We're waiting for maybe 2 more minutes here to allow for 1 or 2 more questions to come through. Seems like there's 2 more people wanting to ask a question. I will try to address these questions to my best knowledge right now. And if we do not answer this, we will basically follow up with you, or you can send us an email and we will try to figure your questions out quickly. One more question here from a designer in Vancouver. Would you see a larger group factor applied for a longer panel-to-panel connection with the same number of screws per length? So if I understand this question correctly, we basically have a 10-foot or 20-foot or 40-foot panel, and we have a larger number of fasteners in this particular panel setup. I would say at one point there is a stop to the group effect because we have so many fasteners engaged in a load transfer that the specimen cannot shift anymore really. So this would be a type of connection. If we have many of these fasteners in there, it seems like the deformations in the connections get very small. We get a very high stiffness and a very high load resistance. And even if we were to have a group action factor of 0.8 or something like that in a connection, we have an overstrength factor of 3 or 3.5. So we would probably still be designing on the safe and conservative end for something like that. Okay, so there's one more question here to create beams. With CLT panels, I assume this is basically a box beam built out of CLT panels or a T-section beam built out of CLT panels. I believe this has been done already, and I also believe that there is actually some test data on this from a university in the United States somewhere. I believe they used some of the fully threaded screws to engage a panel material to a glulam beam and form a T-section. We would have to check into this and see if there is test data available, research paper available to estimate something like this. However, if you are looking at this, you can basically derive capacities and stiffnesses out of the theoretical approaches that already exist. We can calculate the withdrawal resistance in a CLT panel fairly accurately on the conservative end with the design methods that we right now have. And if we basically fasten a CLT panel to a CLT beam, building a T section, we could potentially use the mechanically jointed beam theory, which we have introduced in one of our papers a little bit earlier, late last year, actually late in 2014, to design these connections and estimate the stiffness of the connection system. So if you're interested in looking at this, we can definitely hook you up with the right data on this and propose an approach for you. Okay, I think we have probably answered most of the questions. Again, want to thank you for your attention and hope this was informative for you and we all learned something new from it. Please send us any questions you have on the timber connection systems. We will do our best to answer this, and I wish you have a good rest of the day. Thank you very much for attending. Goodbye.